Swayam Prabha. Digital India. Educated India.
All right, so good morning, good afternoon. Welcome back to our series of lectures on the analysis and design of rigid pavements. We are quite deep and thick into the weeds. Today is lecture number 28, so we are well over 60, about 2/3 along the way. So we are in module 4, which is on the mechanistic empirical design of rigid pavements. So just a brief recap before we jump into the details on where we are in this course. So module 1 was of course just an introductory module. There are two important things we learned in module 1. First of all, in module 1, we learned what are the different types of rigid pavements. So we saw we have JPCP, JRCP, CRCP and PCP, of which JRCP and PCP we don't really talk about in this class. They're rare or specialized applications. We have JPCP, jointed plain concrete pavements, which are by far the most common types of rigid pavements. And so that's why most of the class has basically talked about JPCP. There is CRCP, which is also used. It's not as widely used as JPCP, but it's not a rare thing to use either. We did not talk about it too much except a little briefly in an earlier lecture. But the truth is that JPCP and CRCP, at least as far as analysis goes, design they branch off somewhat, but at least as far as analysis goes, they track very closely with each other. So really, we have been studying CRCP to a large extent as well. It's just that I haven't explicitly talked about it at any point. Now, we also learned in module 1 about different type of distresses. We saw that for JPCP, in terms of distress, we are particularly interested in cracking, that is fatigue cracking or transverse cracking, as well as longitudinal cracking. We are also interested in faulting. And then for CRCP, punch outs are a major distress that we're concerned about. Usually, we are also interested in crack width. Crack width is not directly a distress, but it's a performance measure. It actually determines how long the pavement is going to last, how durable the pavement is. So crack width and punch outs are two important distresses that we are concerned about for rigid pavements, in particular for CRCP. Now, modules 2 and 3 were on the analysis of rigid pavements. That was a lot. We spent roughly a quarter of the class, a little more than a quarter of the class actually, studying analysis and design of rigid pavements, the analysis of rigid pavements. And the reason is that design, especially mechanistic empirical design, is really an iterative process. So we choose some kind of an approximate or a trial test section, and then we run an analysis through it. We look at the predicted performance. We see whether that predicted performance is less than some threshold, and that threshold is more of a policy decision than a scientific decision. We see if it's below a certain threshold. If it is, then we call it an acceptable design. If it's not, then we have to go back. We have to update our trial design. We have to iterate until we get an acceptable design. So to come up with one design, you might have to perform 3 to 4 or even more analysis. So this is why I said that design is repeated or iterative analysis. So it's very important for us to be able to know how to do analysis. Two types of analysis which we looked at, which was module 2 was classical methods, module 3 was using FEM. So classical methods, for example, methods from Westergaard, updated versions of Westergaard. We looked at Freiberg theory. We looked at Tabataba's modifications to Freiberg's theory. All of them basically have given us some nice closed form solutions, some relatively simple formulas that we can calculate by hand. We could calculate with a calculator. We could put it into, say, a spreadsheet and do the calculations. They're not easy equations, as we saw. For example, even with Westergaard's theory, we saw the equations can contain 7-8 different terms. And I had pointed out then that two things. One, be very careful of units. We use mixed system of units in engineering. So somewhere you'll have kilonewtons, somewhere you'll have newtons, somewhere you'll have millimeters, somewhere you'll have meters. Be very careful on the system of units that you're considering. And also be very, very careful about the order in which you're evaluating terms. We went to a somewhat painstaking extent to show you how to evaluate individual terms, first evaluate individual terms, then add them, then multiply them, etc. So we went through this entire process. So this is to say that these analytical solutions, these classical solutions, they are not easy in the sense you can make mistakes while calculating them. But they are easy in the sense that you don't really need any sophisticated computer programming to be able to calculate them. But a shortcoming of these analytical methods, which we discussed, was that all of them eventually are built on a set of assumptions which may or may not be reasonable. For example, all of these solutions are based on the idea that slabs are of infinite size. So if you place a load near a joint, that joint will have an effect on the stresses. But the other joints are so far away that they don't really affect the stresses. There are other assumptions also made related to the footprint, related to the nature of the subgrade, etc. So we saw that while these analytical solutions are useful, and certainly before the advent of computers, they were the only thing we actually had. But the truth is they are not exactly good in the sense we are making a lot of error because of these unreasonable assumptions which are being made. So since the 1990s onwards, when digital computers became widely available, we have been using the finite element method in the analysis and design of rigid pavements. That is true both in India as well as in other countries as well, including the US. So we've been using methods related to the finite element method or generally numerical methods. Now, in numerical methods, the advantage is all these assumptions which I talked about in classical methods, infinite slab, tension, subgrade, etc. All these assumptions which I talked about, which we have to make in numerical method, in analytical methods, these assumptions go away when we work on finite element method or numerical methods. So that's good. What's the downside? The downside is when we do finite element methods or numerical methods, we actually start with the assumption that our solution is wrong. So we even give up on the idea of getting an accurate solution. Instead, we assume that we have a wrong solution, but we also assume that as we discretize our geometry, as we discretize our slab into a larger and larger number of finite elements, then our error will go down. So we start with the assumption that we are definitely going to have an error, but we can eventually make the error very small, maybe 1%, 5%, which is good enough for engineering applications. So that was the advantage of the finite element method. We saw using the finite element method how we can come up with some special plate elements, how we use the Sophie-Germain equation with plate elements, how we can come up with these special plate elements to analyze rigid pavements. We saw how we can use certain special analysis on dowels. We looked at the component dowel model and how we can fold it into a finite element analysis. Most importantly, what we learned in the finite element method is that in its heart, what it's doing, it's taking a continuous equation. It's taking the equations which is a differential equation, the Sophie-Germain equation. It's taking a continuous differential equation. It is discretizing it into a series of a very large number, thousands, hundreds of thousands, a series of a very large number of algebraic equations. And of course, you're not going to solve 10,000 algebraic equations by hand. In high school, maybe you solved 3 algebraic equations by hand, and that itself made you sweat quite a bit. Computers, however, are very good at solving such large algebraic equations. In fact, since the 1950s, we have had very good subroutines and very good codes that can do these kind of calculations. So the truth is, when it comes to finite element analysis, we mostly use a computer to do the analysis, but you should know what's going on under the hood of the computer. Anyway, that is what we studied in Module 1, Module 2, and Module 3. All of that information comes together in Module 4, which is on mechanistic empirical design of rigid pavements. I formally defined to you what is mechanistic empirical design. We'll have a review today. And in the previous lecture, I gave you an overview of a particular implementation of mechanistic empirical design. So ME design is a philosophy of design. A particular implementation of it, probably the most sophisticated implementation in the world, is in the US, and that was developed by an organization called AASHTO, American Association of State Highway and Transportation Officials. They created a design guide. This was around in the late 2000s. They created a design guide which was then called the MEPDG, Mechanistic Empirical Pavement Design Guide. Today it's been renamed as Pavement ME, and it comes with the companion software which also has the name Pavement ME. So the companion software, all of the detailed analysis and discussion which we're doing, the companion software actually takes care of all of that inherently. So it's very easy to actually run a design, despite how complicated mechanistic empirical design is. Using Pavement ME, it's actually very easy for even a student or a new engineer or designer to come up with a design. Of course, gauging the correctness of the design, understanding whether the mathematics is correct and whether the answer will actually work when constructed, that still takes experience. But don't think that mechanistic empirical design is extremely complicated. It is extremely complicated, but the truth is it ideally will be implemented on a computer, so it's not as difficult as it seems. Okay, now in the previous lecture, we've been starting on a series of lectures where we are looking at how the ASHTO MEPDG or pavement ME, and by the way, I'll use these two terms interchangeably, MEPDG or pavement ME. So we've been starting on a series of lectures where we've tried to see ASHTO pavement ME, how does it implement the philosophy of mechanistic empirical design for the analysis and design, or particularly the design of rigid pavements. Design, of course, being repeated analysis. In the previous lecture, we looked at how traffic in particular is characterized. So we saw that in the old empirical methods, traffic is characterized in terms of this thing called a standard axle, or in India, what we call MSA, millions of standard axles. And we saw that it is basically based on this fourth power law, that is the damage which is caused by an axle of weight W is equal to or is somehow related to W over 80 raised to the power of 4, where W is in kilonewtons and 80 is 80 kilonewtons. So 80 kilonewton is what we call a standard axle. So for example, if we have a 160 kilonewton axle, then its damage is going to be, that's double of 80 kilonewton, it's going to be 160 over 80 power 4, that is approximately 16. That is actually exactly 16. So what we say is that one repetition of 160 kilonewton axle is equal to 16 repetitions of a 80 kilonewton axle, and 80 kilonewton axle we call it a standard axle. So in this way, we can look at our entire axle, the axles that we have on the pavement, converted into a standard axle. This is the empirical approach. Why is it empirical? Because this formula, this fourth power law, this is an empirical approach. This is based on data collected in 1956 to 60 in the Asher road test. By the way, it is still used in India in flexible pavement analysis and design, even the mechanistic version of flexible pavement analysis and design. In rigid pavements, however, it is not used, but it is still used for administrative purposes. So it's useful to know what it is, but we don't actually use it in our rigid pavement design. So in the previous lecture, we saw that if this concept of standard axles is not used, then what is used? We saw that we need much more information. In mechanistic empirical design, we need much more information about traffic. We need to know about axle configuration, we need to know about classification of trucks, we need to know about axle load distribution, etc. So there's a significantly greater amount of information that has to be collected when we're doing mechanistic empirical design of rigid pavements in terms of traffic. Now, today's lecture, we are going to move in to talk about climate. We had a discussion on climate, if you recall, back in module 2. In module 2, we had seen how we can take what is climate, what are the different aspects of climate that affect rigid pavements, and how we can take them into account. We looked at how we can do that for analysis. We actually solved an example also for analysis. But in today's lecture, we are going to talk about how climate effects are taken into account in design, in particular in the ASHTO MEPDG design. Okay, and there today I'm going to give you a very brief outline on a particular sort of a subroutine or a program which is contained inside MEPDG, which is the EICM, which is, let me write out the full form, it is the Enhanced Integrated Climatic Model, or the EICM. So the consideration of climate in rigid pavements in pavement ME or ASHTO MEPDG is using this particular sub-program, which is called the EICM. So we'll see some details about it, and I'll start by explaining why do we need it. So what you may want to recall is what are the climate effects on JPCP. Now for details, you want to go back to module 2. We had a couple of lectures where we talked about climate. But putting it very succinctly, there are basically 3 climate-related effects that we are concerned about in JPCP. Curling, shrinkage, and BIC or built-in curling, which sometimes in India we call it zero stress temperature difference. Curling, so what basically happens is curling and BIC are both related to temperature. So when you have a JPCP pavement, it is almost never are you going to have a situation where the top surface and the bottom surface have the same temperature. Either the bottom is going to be warmer than the top or vice versa. So when the top is warmer than the bottom, for example, when you have the sun which is shining, it's going to try to take a shape which is like this. So this concave upward shape, it's going to try to take this type of a shape. or when the bottom is warmer than the top during night, for example, the pavement is going to try to take this type of a shape. And note the exact shape that it's taking. I'm drawing these qualitatively, but really the shape that it's trying to take is going to be changing throughout the day. It is what we call a transient temperature distribution. So some temperature distributions develop inside these pavements. We'll talk more about the nonlinearity of them in a second. But some temperature distributions develop inside these pavements and they are transient in nature. They change not just between morning and evening. They change every hour as the sun is moving across the sky, as you have clouds, as you have rain. You have continuous changes in these temperature distributions and therefore continuous changes in the stresses which is developed as a result of these temperature distributions as well as any external load which has been applied. Those stresses are what we call curling stresses. Whereas if this same phenomenon on temperature distribution is developing, this also happens at an early age when the concrete has been freshly laid and it's yet to assume its full its full strength. In that case also, when we assume some type of a temperature distribution occurs in early age concrete, then it changes our reference state. Our reference state of stress is no longer this flat slab case. It's actually whatever shape the concrete tended to take when it was at its early age and when it just reached its full elastic properties. That behavior is what we described as built-in curling. So you want to go back to that lecture. We had a fairly detailed discussion of the mechanism of built-in curling and how we characterize it for design. I'm not going to repeat it over here, but that's basically what we call built-in curling. So shrinkage and BIC are related to temperature. BIC is basically once the pavement sets, it's one final number which is then present throughout the entire history of the pavement after setting. And curling is a more transient behavior because at every point of time, as the sun is moving, as the clouds are moving, etc., you have differences in curling. Shrinkage we talked about was related to humidity, especially at early age, but can persist later also. When you essentially have at the top of the pavement, a very thin layer at the top of the slab, you have some amount of drying which is happening because the moisture from the surface is being lost to the atmosphere. And then below that you have more saturated conditions in terms of moisture. So moisture gradients, when they are developed, lead to the development of certain stresses. Those stresses are what we call shrinkage stresses. We saw that in general the way shrinkage stresses are considered, and that's how it is done in pavement ME also, the way shrinkage stresses are considered is to convert them into some type of equivalent temperature, which sometimes we may call a shrinkage temperature. Now, this is not a real temperature, this is a fictitious temperature. But because we have such good understanding of how to consider temperature, it is very convenient and easy if we consider shrinkage also as a temperature, and that's why we take this approach. So all three we saw, these are the three different climatic effects on JPCP, which we had a long discussion about in module 2. So please go back and look at that. Also, what we saw is that observationally, the temperature gradients, the temperature distributions which are developed in rigid pavements are almost always non-linear. In particular, I had mentioned, so for example, what I have over here, I've got Z over H. So this is through the depth of the pavement where Z is equal to 0 is along the neutral plane. So basically, if this is my pavement, then this is Z. This is the top surface. This is the bottom surface. So Z over H over here is the neutral plane is always at H over 2 for plain concrete. So the Z over H over here is minus 0.5 because it's pointing downwards, and here it's plus 0.5. So here basically I've plotted what is a distribution of the pavement, what is the distribution of the temperature through the depth of the pavement. And this is actually based on a realistic case. It's based on some earlier work which I had performed. As you can see, it's pretty non-linear, and the shape of that non-linearity is also changing during the day. We talked about the fact that this non-linearity is usually very well approximated by a quadratic distribution. If not quadratic, cubic will basically get you to an R square of maybe 0.99, which is more than sufficient for our applications. So we saw that these temperature distributions tend to be highly non-linear, quadratic or cubic in nature. And what we also saw is that these non-linear temperature distributions, and I emphasize again, shrinkage is built into this. So shrinkage we just add as a fictitious temperature, which is also non-linear, and then we use the same analysis for shrinkage as well. So these non-linear temperatures, so the actual temperature distribution in the pavement is going to be non-linear. This is always with respect to some reference temperature T naught. It doesn't actually matter what T naught is, it's just you should know that there is a reference temperature. So what we saw is this can actually be decomposed into three effects. So it can be decomposed into three temperature distributions, which represent three different types of effects of stresses which are developed inside the pavement. The first is a constant temperature component, Tc. It's linked to a uniform expansion and uniform contraction of the slab. We saw that in general, we assume that there is no stress which is developed due to this uniform expansion and contraction of the slab. A little bit of stress could come in the form of any friction from the base. That is, the base layer is resisting that expansion contraction, but it's usually so small that it's more or less negligible. The second component is what is a linear component. So we can divide this into a linear distribution like this. And this is actually what's going, so this is TL as we pointed out back then. This is actually what causes curling. So this temperature distribution says that relative to the reference temperature, my top surface has a higher temperature than my bottom surface, which is exactly what I showed in this slide. So top surface has a higher temperature than bottom surface. On its own, this linear temperature distribution does not generate any stress. When a load is applied to it, for example, in this case, this is the position of the critical load, or if you have this type of configuration, then this is the critical position of the load. When a load is applied to it, which is restraining the pavement from taking this type of shape, that's when some type of stress develops, which is what we then call curling stress. And then we saw that there's a third component, which is this non-linear component of temperature. So it's a non-linear component of a non-linear temperature. It basically exists because for these JPCPs, it has been observationally observed to be correct also, that a plane section basically remains plane before and after bending. Now, a non-linear temperature distribution is going to try to create a non-linear cross-section. But our cross-section must remain plane or linear. And so in order to force the cross-section to remain plane, additional stresses are developed. So we are kind of restraining it from assuming a non-linear shape. In doing that process, an additional stress is developed, which we call an eigenstress. So it's created due to this non-linear component. The eigenstress does not depend on any external loading. It is an inherent stress which is present inside the slab. Okay, so we saw all of this. And furthermore, so we saw all of this in our analysis lecture. Then we saw an example also where I gave you one of these nonlinear distributions. I showed you how we can do this decomposition. I showed you how we can calculate the eigenstresses, etc. So please go back to that lecture in module 2 if you want a revision on these topics. Let's now come back to the concept of design. So one thing which I had pointed out earlier to you in the previous lecture on design is, what is the difference between analysis and design? In analysis, we know everything about the pavement. So relative to our discussion over here, in module 2, which was on analysis, I showed you, given a temperature distribution for a given thickness of a pavement, given a temperature distribution, you could then go and do the remaining calculations. These calculations which I just showed over here, you could calculate eigenstresses. Technically, with any finite element program, you can also calculate what are the curling stresses. The expansion contraction stresses we generally take to be 0. So in analysis, you are given the load, you are given the material properties of the pavement, you are given the temperature distribution critically inside the pavement, and then you can do the remaining calculations. Now, what about design? I mentioned in the previous lecture, design is the exact opposite. When you are designing a pavement, you don't have a pavement. The pavement doesn't actually exist yet. That's why you're designing it. When you don't have a pavement, you don't have a thickness, you don't have a load. You don't have any temperature distributions. In other words, you don't even know what the climatic effects are. You don't know what inputs to provide to calculate these stresses. Now, why do we need these? Here is an outline which is basically of the MEPDG. So this is a general outline of the MEPDG process. We'll see more details about this general process in subsequent lectures, but let me just point out that basically we provide some input data. We have to calculate some environmental effects. This generally goes down to some moisture and freezing and thawing conditions. We have some pavement response model. That is our finite element model. We're calculating what the stresses and the deflections are. We have some distress model, which is basically our transfer functions. And then we make some performance predictions. We also have some material characterization on the way. For each of these steps between input data, in calculating environmental effects, in calculating pavement response, we require climatic inputs. So climatic inputs are extremely important in the mechanistic empirical pavement design guide because they essentially are required as an overall input. They modify the environmental effects and the material properties. They also modify the structural response of the pavement in terms of the stresses which are developed. So we need to have a way to calculate these climatic effects for a pavement, for designing a pavement which doesn't even exist yet. So this preceding discussion which we had, it's fine for analysis. But as I pointed out, in design, we don't have a pavement. So how do we get a temperature distribution for a pavement which we don't have? If you recall in module 2, the example which we had done, I had specifically said that there is a pavement and some thermocouples were placed inside the pavement. So it's already there. We simply place some thermocouples, we measure the temperature, and then we did the rest of the calculations. If you don't have a pavement, you're not going to apply a thermocouple to anything. So then how do we obtain a temperature distribution when we don't even have a pavement? Furthermore, what are the factors that affect the development of this temperature distribution? If we have a pavement, we can simply go out and measure its temperature distribution. But if we don't have it, can we at least know what are the factors that will affect the temperature distribution? Okay, so when we are then doing design of rigid pavements based on climate considerations, we broadly have two approaches which can be used, which are empirical design approach and a mechanistic design approach. Again, what I'm trying to say is that if you are trying to design a rigid pavement and you want to design the climate considerations, you want to do climate considerations within that design, you basically have to know what is the temperature distribution inside a pavement which doesn't exist yet. So to do that, there are two philosophies which we can use, the empirical philosophy and mechanistic philosophy. Now, please don't get confused here. We are still talking about mechanistic empirical design. Within mechanistic empirical design, some aspects of our design can be mechanistic, some aspects of our design can be empirical. One aspect of design, which is the topic of today's lecture, is on consideration of climate and climate effects. So we can model this particular aspect of design still within the overall mechanistic empirical framework. We can model this particular aspect of design either empirically or mechanistically. Now, the empirical approach is to supply some design temperature distribution that we say that, okay, in this part of the country, this is a typical temperature distribution. In another part of the country, this is the typical temperature distribution. For a particular season, this is the temperature distribution. During the morning, this is the typical distribution. During the evening, this is the typical distribution. So the empirical approach is to actually go out, collect all this data, and supply some so-called typical values of these temperature distributions. That's the empirical approach. And this, by the way, is exactly what we do in the Indian approach. So although in India also we use a mechanistic empirical design, our consideration of climate still follows an empirical approach. And we'll talk about this much later when we get into lectures on IRC 58. Okay, the other approach is the mechanistic approach. The mechanistic approach is basically, the idea of mechanistic approach is to use physics. So let us use physics to calculate what is this unknown temperature distribution through our design pavement. And that's basically what the pavement ME does. So in the mechanistic approach, we have to develop a physics-based model for temperature in JPCP. Now, generally, when it comes to temperature that is related to heat, and for those of you, most of you, I'm assuming, are civil engineering students. So in civil engineering, we don't learn a whole lot about heat and temperature, etc. So if any of you are mechanical engineers, this would be a little more familiar to you. But for the rest of you, this might be a little bit new. I'm not going to go into all the detailed derivations. You really want to take a formal course on heat transfer if you're really interested to go into all the physics of the problem. But basically, if we have a body, if we have any body, and we want to know how is the temperature in the body changing with time and space. So how is the temperature what is the temperature at different points, and how is the temperature changing with time? Then the governing equation of this particular system is called the Fourier heat equation. The Fourier heat equation is trying to solve for T. T is a function of x, y, z. So it's a function of space. It's also a function of time T. It's a function also of the certain material properties of the structure or of the material. Those material properties, and we had seen this in one of our earlier lectures, they are the thermal conductivity K, the density rho, and the specific heat capacity Cp. So density, so conductivity, density, specific heat capacity, or heat capacity actually in this case. These are the three variables that we are interested in as material properties or constitutive properties for the Fourier heat equation. So the derivation of the Fourier heat equation is not particularly important, but this is what the Fourier heat equation is. By the way, for some of you who are a little bit unfamiliar, this del operator, right, this is the gradient operator. So this is basically del over del x, comma del over del y, comma del over del z. So this is a gradient operator. So we have a del dot of k gradient of t. So here we are taking the gradient of t, that's a vector, multiplying it by k. Then we are taking a dot product of it with delta. So it's going to give us a scalar, and then dividing it by rho Cp. Okay. Now, this is a differential equation. If I'm sure most of you have taken a course at some point on differential equations, you will know that to solve this differential equation, so this differential equation is telling us what is the temperature distribution inside the body in space and in time. But in order to actually calculate it, we also require certain boundary conditions. That is, we need to know that at the boundaries of this system, so these are the boundaries of the system, at the boundaries of this object, what's happening? What are the conditions at the boundary? Based on those conditions of the boundary, this equation can be solved. So let's think about it. So that was in general, broadly speaking, for any body. That's more of a mechanical engineering discussion. Let's get back to rigid pavements and JPCP. What are we solving in JPCP? So again, JPCP is a multi-layered system. So we might have a PCC surface, we'll have a base course, maybe we'll have a sub-base course. Eventually, we will have a subgrade, which is much bigger than the other layers. So we have this sort of a system. One major assumption we make in pavement engineering, so generally for a three-dimensional body, which is, and a pavement is a three-dimensional body, we assume the temperature is a function of x, y, z, and t, Ts time. So we assume that it varies in all three dimensions in space. One major assumption we make in pavement engineering, and it's been seen to be a pretty good assumption for design purposes, is that we assume that the temperature distribution only depends on z and t, where z is this vertical coordinate. So we assume that there is no dependence of the temperature on the horizontal coordinate, that at any point along the pavement within a reasonable length, at any point along the pavement, if we drill down and we put thermocouples, we will get more or less the same vertical distribution of temperature at the same time. So that's a major assumption which we make, which we'll see that has certain effects on this equation. This equation simplifies quite a bit once we make this assumption. So then if we look at this, now what boundary? So now we have reduced this multi-layer three-dimensional system into a one-dimensional system that consists of several layers. In this case, what are the boundary conditions that we require? We need a boundary condition at the top of the pavement. That is the part of the pavement that the cars are going on, that pedestrians are on, etc. We also need a boundary, and this we generally might show as z is equal to 0 in this case. And we need a boundary condition at the bottom of the pavement. Now, in theory, the bottom of the pavement is still the core of the earth. It goes all the way down to the core of the earth, but we don't do that sort of modeling. We typically we consider the bottom of the pavement to be roughly 1 meter or 1000 millimeters into the subgrade. So we say that for the purposes of calculating temperature or trying to figure out the effect of temperature or climate on pavements, we assume that the bottom of the pavement is 1 meter into the subgrade, and then we stop it over there. So at z is equal to 0 and at z, which ends at 1 meter subgrade, so it's the sum of all the thicknesses plus 1 meter for the subgrade. At these two values, we would like to specify certain boundary conditions. What are the appropriate boundary conditions that should be specified for JPCP pavements? What physics describes the energy balance at the top and bottom of the pavement surface? So there are many ways to model this. There are many different approaches. There is a European approach. In the European approach, what they actually do is they specify a surface temperature. So they fix a value of surface temperature over here into maybe some value T naught. They fix some other value at the bottom, maybe we'll call this TE. They fix some value over here, and then they solve this equation in between. That's one approach. The EIC, the pavement MES approach actually is probably the most sophisticated approach in the world. It uses a different model which is called the Enhanced Integrated Climatic Model, EICM. The EICM is a numerical model right? That means we are making some numerical approximations. It's not quite finite element modeling, but again, we are solving this equation. By the way, the equation in 1D, it becomes like this. So it's del over del T is equal to 1 over rho Cp del over del Z, because now it's a 1D equation, del over del Z, K del T over del Z. And if you assume that K is constant for a particular layer, we can actually take it out and we'll get this is equal to K over rho Cp into del square T over del Z square. K over rho Cp, sometimes we give this the symbol alpha, which we call the thermal diffusivity. I had talked about the thermal diffusivity and these properties as well as a couple of other properties of rigid pavements back in an earlier lecture in module 1. It was actually a materials lecture in module 1. So I do recommend you want to go back and just review your notes from that lecture. A lot of concepts will come back in this lecture. Okay, but continuing from what we were talking about. So the EICM, the Enhanced Integrated Climatic Model, is a numerical model. So it's not solving the temperature at every point. We actually have the pavement. Again, it's a 1D model. We are discretizing it into a discrete number of nodes, and we are solving the equation at the nodes. The temperature in between the nodes, we have to assume has some type of a shape. Now, the EICM is therefore, that's a numerical model that we're solving the solution at some discrete nodes. It is an explicit finite difference based model. Now, this is not a class on numerical modeling, so I'm not going to go into details of what exactly it means to be explicit and what is a finite difference based model. So this I will leave you to you as self-study. If you're really interested to understand these terms which I've put in italics over here, explicit finite difference, I'll let you figure it out. It's not important in this class to understand. So the EICM is a numerical explicit finite difference based model. It solves the Fourier heat equation in 1D. So the assumption is that it is a 1D problem. So this is the equation which I've written on this slide. It's basically simplifying this earlier equation. It's simplifying it and solving a simplified form of this equation with appropriate boundary conditions to calculate the hourly temperature distribution in the PCC slab of JPCB hourly. So it basically tells us at each hour what is the temperature at certain points or nodes inside the slab. From there, we do further calculations, but the EICM just gives us that particular calculation. So what's clear over here is, we know what equation we're solving. The technique to solve it is this explicit finite difference scheme, which it's not important for you to know what that is, but it has appropriate boundary conditions. What are these appropriate boundary conditions? That's what we're going to talk about in the next few slides. Okay, before we go into the mathematics, let's just think about it. Let's say you are standing on the road, standing in the middle of a road. Please don't do this in practice unless there's no traffic. But suppose you're standing on the road, and then I ask you, what are the different types of energy fluxes coming on the road? In other words, what energy is coming on the surface of the road, or what energy is coming out of the surface of a road? All right, so this requires you to go back to a little bit of high school physics and remember a few concepts from there. So first of all, the biggest source of energy on the planet is the sun. So the sun is shining and beating down on the road. Of course, the amount of sunlight coming may be limited, of course, by the time of the day. So early morning, you won't have too much sunlight. Late evening also, you won't have too much. Of course, obviously in the night, you don't have any sunlight. Afternoon, you'll have a lot of sunlight. But then it also depends on clouds. And clouds in turn have certain seasonal and daily variations in the amount of cloud cover that we get. So the amount of sunlight falling on the road is not a constant. But certainly we understand that one of the biggest sources of energy on the road surface is the sun and sunlight which is incident on the sun. Okay, what else? You may have studied a particular phenomenon in high school which is called convection. Let me write it down. So there's a phenomenon, I've got it here, which is called convection. So convection is basically when you have a surface and then when you have a solid surface and you have a fluid flowing over the surface, then due to the movement of the fluid particles, you have an exchange of heat between the fluid and the solid. That phenomenon is called convection. So what is the fluid which is flowing over a road? The wind, obviously air, wind, and it's flowing at a certain speed. So the surface of the road is exchanging energy with the air above it used through the physical process which is called convection. There is a third physical process which again I hope you learned in high school, which is called radiation. You may recall that any body whose temperature is above 0 Kelvin, so above absolute zero, emits a certain amount of radiation. It exchanges a certain amount of radiation with its surroundings. So what are the surroundings we're talking about? The pavement surface is not at 0 Kelvin, it's obviously much higher than that. You have some surrounding air, buildings, etc., which also have a higher temperature than 0 Kelvin. So there is a continuous exchange of long wave radiation between the pavement surface and its surroundings. This phenomenon is what we call radiation. So there are a few more phenomena that you could also think of, but broadly, there are three types of physics that we are interested in at the surface of the pavement. So now let's go back to this equation. So if I ask you the question, what is the total amount of energy entering into a pavement? This is what we sometimes write as QG. QG, by the way, stands for ground heat flux. That's the G stands for ground. So the ground heat flux, that is the amount of radiation which is going inside a pavement. By the way, if that number is positive, it just means it's going out of the pavement. So when I say inside, I'm just putting a sign convention to it. So the amount of radiation going inside a pavement, that is shown using this term, that is minus K del T over del Z at Z is equal to 0. So this is just a mathematical formulation that any flux is minus K del T over del Z specified at a particular point. So the surface flux, as we call this, surface flux or the ground heat flux, this is the amount of incoming solar radiation Qi, but not all of the solar radiation is going to be absorbed by the pavement. If you go back to lecture 4 in module 1, I had introduced the concept of the albedo. The albedo was the reflectance of the average solar reflectance. So if, for example, I told you that for concrete pavements, a typical albedo is 0.3. What that meant is 30% of the energy is reflected and 70% of the energy is absorbed. So if I'm interested in to know what is the magnitude or the quantum of solar radiation which is being absorbed into the pavement, then I take the total amount of solar radiation and I multiply it by 1 minus the albedo. This alpha S over here is a symbol I'm using for albedo. So 1 minus albedo, which in some literature you will see this called as the absorptivity or absorptance. Absorptance actually means something slightly different, but this is the absorptivity of the pavement. So 1 minus albedo, absorptivity. So we multiply the amount of solar radiation by the absorptivity. That tells us what is the total amount of solar radiation being absorbed into the pavement. We take into account QC. We'll see the formula for this in a second, which is the energy lost by convection. And then we have the energy lost by radiation. So on the surface of the pavement, this provides our boundary condition. The boundary condition is what we call, let me write it here, what we call a surface energy balance. Right? Surface energy balance, that is what is the total amount of energy, net amount of energy, which is entering the pavement. That is our boundary condition which we supply at the top of the surface. Okay, just to give you the formula, it's not very important to know the formulas, but just to give you the formulas, this QC, this was this convective radiation term, this is equal to H, I should write this as HC actually. So HC into TS minus TA. TS is the surface temperature of the pavement. So you've got the pavement below this, etc. You've got these multiple layers. This surface temperature we can write as TS. This, by the way, can also be written that TS is equal to T at Z is equal to 0. So same thing. So TS and the air temperature at some distance, generally it's assumed 1.5 to 2 meters. So the air temperature is around 1.5 to 2 meters above the pavement, and that we give the symbol TA. So QC is HC into TS minus TA, where HC is what we call as the coefficient of convection. Again, I hope you studied this in high school. So this is called the coefficient of convection. This particular formulation, that QC is equal to HC into TS minus TA, this is actually called Newton's law of cooling. Yes, same Isaac Newton. So this is based on Newton's law of cooling. As far as radiation, the radiation QR is epsilon sigma TS power 4 TA minus 4. This is again an equation I hope you studied before. It's called the fourth power law. So it says that the radiation is proportional to the difference of the fourth power of the temperatures between two bodies. Keep in mind, this temperature is the absolute temperature. So this has to be in Kelvin. That's a common mistake that many students make, not to convert it to Kelvin. So here we see that we have two terms over here. One is we've got this epsilon. This also I had defined in lecture 4. This was the emissivity. So if you recall in lecture 4, I had defined two types of optical properties. One was the albedo one second was the emissivity. Both of them you see are basically coming in at this surface energy balance. This sigma over here, 5.67 10 power minus 8 watt per meter square per Kelvin power to the raised to the power of 4, that is the Stephen-Boltzmann constant. Again, I hope you studied this in high school. So this is how you calculate the exchange of exchange of radiation, exchange of energy due to radiation, exchange of energy due to convection, and the amount of solar radiation falling, which of course has to be multiplied by the absorptivity. Keep in mind, Qi is going to be 0 in the middle of the night, obviously. We do sometimes provide some empirical corrections for clouds as well. It's not important to go into all those details at this point. So now that we know how to calculate it, this equation gives us the energy balance at the surface, which in turn gives us our boundary condition at the surface. This is how the EICM does it. We still have one more boundary. That is the boundary at the 1000 millimeters or 1 meter into the subgrade. That's where we consider our pavement has ended for the purpose of the EICM. That is another boundary. We have to specify one more boundary condition there. Now, that is an open question of how to do it. At the bottom surface, which is deep inside the subgrade, and by deep, I basically mean 1 meter. Deep inside the subgrade, it's not very clear what the boundary condition is. So in the previous example for the surface boundary, I had told you to imagine yourself standing on the road and what are the different physics going on. So I hope it was a little bit intuitive based on what you've done. But I'm definitely not going to ask you to dig yourself deep into the road and then imagine what's going on down there. So it's a little bit unclear what that boundary condition at the bottom surface should be. It turns out, however, that for JPCP, it does not really matter. It's not a very important boundary conditions because again, for JPCP, we have a multi-layered system. We are really interested in the temperature distribution at the top. The remaining, we are not too concerned about it, which means we can start accumulating a little bit of error as we go deeper. It's not too important as far as the performance of the JPCP itself is considered. There are generally two approaches which are used. They're not entirely made up. There is some good basis on where these two assumptions come from, but they're pretty simple assumptions. The two assumptions is an adiabatic or small flux assumption, which is adiabatic basically says that the flux minus del T over del Z, this time as Z is equal to, let's say Z is equal to Z naught. So that's at the bottom of the pavement. So at the bottom of the pavement, we could say this value is equal to 0. That is, there is no exchange of very deep into the pavement. There is no exchange of heat between the pavement and the rest of the ground. If you don't like that, if that seems a little bit too strong an assumption to make, some assumptions make a very small amount of heat flux. So let's say this could be, let's say 0.01 watt per square meter. So that's an additional assumption. So either we say that there is no very deep into the pavement, there is no heat exchange, or there is a very, very small heat exchange very deep into the pavement. So that's one assumption. That's an adiabatic assumption. The second assumption is the constant temperature assumption, that we assume that deep into the pavement, you assign some constant temperature. This is the approach which is used by the EICM, this constant temperature approach. And what is that temperature? There are good reasons on why this is correct, but what they use is they assume that that constant temperature is the average annual air temperature. That we say that very deep into the ground, the surface temperature, the temperature of the ground is constant, and that temperature is equal to the average annual air temperature. There is some experimental data that supports this, although it's questionable if the instruments are sensitive enough to be able to register this. And there is some good, not physics, but sort of intuitive understanding on why this is the case. It's not important in this class for you to go into all those details. But in summary, what I want to say is that these are the two the boundary condition at the bottom, which is 1 meter into the subgrade. It's not very clear or obvious what to use. It's not very important either, as it turns out, for JPCP. So either you can use this adiabatic assumption, or as the EICM does, you can make an assumption about some constant temperature. It does not make too much of a difference at the end of the day. Okay, so now we understand what was the equation that the EICM is solving and what were the boundary conditions. I also mentioned we solve it using an explicit finite difference scheme, which is not important to understand. All you understand that it's a particular numerical approach. We'll see a little bit more about it before we conclude today's lecture. Now, I want to talk a little bit more. So I gave you a very broad overview of the EICM. I did miss a couple of important points, and I think it's important for you to at least be aware of all these points. So the name, Enhanced Integrated Climatic Model. Just look at the name. So it's a climatic model. It's an integrated climatic model. So apparently it's integrating something. Integrate as in to put something together jorna basically. So it's to put something together. And some kind of an enhanced integrated climatic model. So obviously it's better than some other model, which was the integrated climatic model. So the name itself tells you that there seems to be a little bit more than meets the eye on this particular model. The EICM is actually an amalgamation or a combination of three models. There was the first model, which is the climate materials structure model, which is the CMS model. This was developed by then student and later Professor Barry Dempsey in the 1960s in the University of Illinois. I actually had the pleasure of having a fairly long meeting with him and looking at his original notes and original thesis. So this was the original CMS model. The CMS model is basically what I defined here. All this discussion I had on this particular Fourier heat equation and then the surface boundary condition, this was all the CMS model. An additional model was also developed, which is called the ID model, the infiltration drainage model. The infiltration drainage model was basically also taken into account that if you had a pavement surface, this was for both rigid and flexible, by the way, if you had a pavement surface and you had some cracks or you had joints and some amount of moisture infiltrated into the joints, then what would be the moisture distribution in the subsurface layers? The surface layer is not going to be affected by moisture, but the base, sub-base, how are those layers affected by moisture? So that was the infiltration drainage model. These were two separate things. The temperature distribution was one thing, and the effect of infiltration and moisture distribution were two separate things. This was called these two together. The CMS model and the ID model together were called the integrated climate model. Later on, a third model, which was developed by what was called the CERL, Cold Regions Research and Engineering Lab. This is a US Army lab actually in the US. They developed a model that also took into account, because it's a very cold place, they took into account what happens when the moisture inside the ground starts to freeze. And what are the additional effects which are caused by what we generally call as freeze-thaw effects. Not particularly important in most places in India, but you should just know about it. So that was the CERL model. So the ICM model plus the CERL model created the enhanced integrated climatic model. So strictly speaking, the discussion I had previously where I talked about these temperature distributions, this surface boundary condition and the Fourier heat equation, strictly speaking, that's the CMS model. It is pretty much good enough for a lot of applications, but it's not the EICM. The EICM is actually not a temperature model. It's a coupled temperature and moisture model. So it's solving not just for temperature, but also for moisture. And it does the following. For in paved layers, that is layers which are made of some kind of a paved material, both bituminous layer as well as concrete layer. It could also be a CTB, cement treated base, or some other kind of treated base. For these paved layers, basically we don't have any moisture. We assume that these layers are not going to hold any moisture. It is only doing temperature calculations. That is, the CMS model is used exclusively for paved layers. But for aggregate layers, GSB, granular subbase, subgrade, etc. For these aggregate models where we do expect moisture, we expect movement of moisture, and we expect temperature as well. In that case, both temperature and moisture are modeled. So here we use the Fourier heat equation, right? Fourier heat equation. We use the Fourier heat equation here because it was only modeling temperature. So we have full understanding of what that is at this point. What about this? How do we model both moisture and temperature? And they're coupled between the two. So as you have temperature changes, you also change the properties of moisture, and that changes how moisture is moving, and vice versa. Okay. For the paved layers, we're basically solving the Fourier heat equation. We already saw everything about that. For aggregate layers, however, it's a bit more complicated. There is a particular model developed by two gentlemen, Philippe and de Vries, in 1957. So these were two European scientists actually. So published in this journal, which was called The Transactions of the American Geophysical Union in 1957. The title tells you sort of everything you need. Moisture movement in porous materials under temperature gradients. Porous materials is referring to these aggregate layers. Moisture movement in those aggregate layers under temperature gradient. So we are looking at some sort of coupling between temperature T and theta. Theta, by the way, I'm saying is the moisture content. So some equation which is coupling temperature and moisture content, and you can read the paper. This paper is actually out of copyright, so you can freely download it. So you can read the paper and you can look at it and try to understand it. It's fairly complicated. You need a fair amount of knowledge in both mechanical engineering as well as numerical modeling to be able to understand this. But this is basically what the equations look like. So the first equation is a moisture equation. It's an equation in theta, but it includes a temperature term. The second equation is a temperature equation, and you'll see that this part of it, at least this part where this lambda was k previously, at least for this part, we saw this before. But there is an additional factor over here which takes into account moisture. In particular, it takes into account moisture when it's in vapor condition. So the EICM model for those aggregate layers is actually a multi-physics model, that is, it's solving for both moisture as well as temperature. It's also solving a multi-phase model. It's taking into account liquid phase as well as vapor phase. It is fairly sophisticated. It's not very important for you to understand all the details of this. I just wanted you to know that this EICM, which is part of Pavement ME, it's quite a sophisticated model. And if you had to solve this by hand, it would essentially be impossible. Fortunately, very smart people have already done it and developed this tool. The last thing I wanted to talk about is this discretization. So I had mentioned previously that the EICM is a finite difference model. It's the explicit part I'm not going to discuss over here, but it's a finite difference model, which is a numerical model. So if we have a continuous, it's a 1D model. So if you have a continuous pavement, we are no longer solving it at every point. We are discretizing it into a series of nodes, and we are solving for the temperature at those nodes. Now, the finite difference model is different from the finite element model. I don't have time to explain the difference, but we basically make some kind of an assumption about how the gradients vary. So, example is del T over del Z square, which is a term we get in the Fourier heat equation. This may be approximated using some central difference scheme like this. Not important. You'll want to take a class to understand more on this, but just understand we are solving it not at every point, but at a discrete set of nodes by making an approximation of the type as shown over here. Now, so one thing to understand is then we are solving it at a discrete set of nodes. Now, generally, we would like to solve in such a way that we are capturing the variation in the temperature distribution. So the temperature distribution at the surface, so along the PC surface, we tend to have a very large temperature distribution. It's very non-linear. But as you go further deeper, it starts becoming more and more linear. So what that means is near the surface, we have large gradients. And so we would like to have a finer set of nodes. Away from the surface where the nodes are getting deeper, we have smaller gradients. So we would like to have a coarser set of nodes. And of course, we generally go down in the EICM, we go down to a depth of 1000 mm for the subgrade. So we end it at 1000 mm, even though the subgrade technically is even deeper than that. So here is an example. So these nodes, sorry, it's moved a little bit, but these nodes basically, this is at the surface, this is the next one. So you'll see for the first two layers, we have a relatively fine set of nodes. As we go down deeper, we can have a coarser set of nodes. So that is what the EICM does. So it's not a uniform distributed set of nodes. We have a finer set of nodes near the surface, coarser set of nodes below it. The exact position of the nodes, of course, depends on the thickness. So that depends on what thickness you're modeling, and there are ways the EICM places nodes. After calculating the temperature at each nodes for every hour of the analysis period, so that's 24 hours a day for 365 days a year for 30, 40 or 50 years. It's a lot. So after calculating a temperature distribution at every such hour at each node, the EICM interpolates those temperatures to 11 evenly spaced points. So regardless of where these actual nodes are, it will just interpolate it to 11 evenly spaced points in the PCC layer. And then that gives us the temperature, the non-linear temperature distribution in the PCC layer we then have at these 11 evenly spaced points. And then the rest of the calculation proceeds as we did previously. That is, you decompose it and calculate the stresses accordingly. So that's the general approach of the EICM. Thus, the inputs needed by the EICM are the layer thicknesses and the properties. Again, we talked about this in an earlier lecture in module 1. And then we need weather conditions. We need that surface condition. We need the humidity, air temperature, humidity, wind speed, etc. So we need a lot of weather related data, which could be obtained using measured data. That used to be the practice, or it can be obtained using some reanalysis data set, some sort of synthesized data or numerical data, which, by the way, you can also download freely. So the last slide I'll leave you with, if you want to download some of this weather data and see how it actually is used without running the EICM, link over here from InfoPave, where you can download some of the data which is used for free from anywhere in the world. Okay, we are almost done with looking at temperature and climate characterization. The only problem is we looked at temperature and climate separately. When we talk about curling, we know we have to look at them together. They together lead to curling stresses. As it turns out, when we have to consider them together, it leads to some additional complications which have to be dealt with. We'll look at that in the next class on the topic of linearization, or what is called thermal linearization. Thank you.